Welcome to Chapter 5. Chapter 5 is about network address translation for IPv4. First, let's talk about a little background. Since 1981, there has been available 4.3 billion IPv4 addresses. The exhaustion of these addresses was estimated before year 2000. IPv6 is a long-term solution, and a short-term solution is NAT and the RFC. The RFC is like the division of the private internet addresses, which came in Class A, Class B, and Class C. Some facts are that there are not enough public addresses available. Because of the short-term solutions, networks commonly use private ones. They use private addresses for local communication, but these addresses cannot be routed to internet. Translation is needed, and there is the space for NAT to NAT does it. There's also the fact that a unique IPv4 address can support thousands of private ones. NAT is primarily used to conserve IPv4 addresses. It translates when needed. It uses a pool of public addresses. This can change. We're going to see that. And it's used by the border router. The border router is like the router, as we can see in the big picture. It's the router that divides the private address space from the public address space. This is a common topology most of us may found at home, without the switches, of course, of a stop network, which is a network that only has one exit point to the internet. What R2 does as a NAT router is that it translates public addresses into private ones and private addresses into public ones. There are several types of addresses. The first one is the inside address, which is an address of a device that it's going to be translated by NAT. An outside address, which is a destination device address, commonly referred to a public address. A local address, which is any address inside the network. And a global address, which is any address outside the network. All these terms depend a lot in perspective. What I mean for this is that it depends what are we seeing and where are we standing. It's the definition or the type of address an address might be. In this example, we can see that an inside address can be the one found on PC1. It's a private address and it's inside the network. An outside address might be the web server, which has a public address and it's outside the network. There is some terminology we need to start knowing because NAT works around this. All the types of addresses are based on perspective. That's a fact and we cannot change it. Addresses can be considered as inside local address, an inside global address, an outside local address, and an outside global address. Let's go slowly in this step. As we can see in the image, we have several addresses. And inside local, if we go from the top to the bottom, we can see that inside local, it's considered to be the PC1 private address, and an outside local can be considered that the private address was translated to a public one, and it's the pink one. That address, it's an outside local. It's local because the router R2 assigned it to the private address, but still it is a public address. An inside global address can be considered to be the web server, but that web server can also be considered as an outside global address. Most of the cases, the inside global is going to correspond to an outside global address, but that's not every time. So we need to be careful from where are we standing to see and to determine which type of address an address will be. Well, here's a quick video of how NAT works. PC1 sends a packet with a private address which reaches R2. R2 checks its NAT table and assigns a public one so the packet can go through the internet. The web server answers to the public address and sends it back. So router checks the public address and translates it to a private one so the packet can reach and move through the private network and reach the PC that sent the packet. There are several types of NAT. The first one is the static NAT. It's configured by the network admin and it's like kind of a special NAT. Each private address has its own public address. I mean, no public address has two private addresses or the other way around. Many public addresses are needed and web servers with consistent addresses use it commonly. Here we have the table or the image with example. If we can see the static NAT table, we can see that the inside local addresses or the private ones, each one of them has its own inside global address or public address. This means that for every device connected to our inside network, we have to have a public address available for them. It's like 1-to-1 ratio. Then we have the dynamic NAT. Dynamic NAT works like the static one, using a pool of public addresses, but it differs on how those addresses are assigned to the private ones. It uses a technique named as first come, first serve, and public addresses are free to be assigned. This works a lot like DHCP. We have a pool of addresses, and every time a private or an inside address wants to communicate to the outside, sends its packet, and when the packet reaches R2 sees its dynamic NAT table or IPv4 NAT pool and sees which public addresses are available or are not being used by another private address. So the packet is assigned to that public address. As we can see, the network 192.168.10.12 is already using one of the public addresses. So in case the server wants to connect to the internet, the next available public address is going to be assigned to his own private address. Finally, we have the port address translation, also denominated as PAT. PAT is one of the most used NAT services because it works with port numbers instead of public addresses or several public addresses, and uses the TCP UDP port numbers. And here's a quick bit of how PAT process works. Sorry about that. And here it is. We have that both computers want to send some packets. These packets, well, before they're translated, here they are. Here it is. Before they are translated, both are using their own private addresses, but with different ports. The first one is using the port 1555, and the second PC2 is using the port 1331. The destination addresses are two different servers, server 1 and server 2. Sorry about that again. When both addresses reaches the router sees its NAT table and changes for a public address to correspond with each packet. The difference here is that there is only one available public address, which is the one that terminates in 226. The difference here is that with the address it comes the port. So one packet has the same public IP address, but it has the different port. As we can see, the one above uses the port 155, such as the PC1 was using, and the lower one uses port 1331, such as PC2 was using. What this does is that, well, packets are sent within the same public address but with different ports. But what if, well, in the case a port is already being used, in this example we can assume that, well, as we can see in the video, that PC1 is sending a packet from its own private address with a port 1444 and wants to communicate to the internet. So it reaches the router sees its NAT table and assigns the inside global IP addresses it needs with that port, with port 1444. The packet goes to the internet, and well, PC1 just waits for the reply. But in the meantime, PC2 wants to send the same packet. Well, not the same packet, but sends a similar packet with its own private address, but it uses the same port as PC1. So, well, you may think that the router is going to have trouble, but instead the router assigns the packet a different port number. In the NAT table, he knows that he assigned a different port number. In this case, he assigned with the public address the port 1445 instead of the 1444. But in the table, it keeps whenever he receives a packet with the port 1445, he knows he has to forward that packet to PC2 instead of PC1. That's the magic of PAT. PAT can, in case a port number is used, he can automatically assign new ports, but without losing the original port the packet was meant to. Here is a comparison between NAT and PAT. NAT, as we can see, uses inside global address pool. It doesn't matter if it's static or dynamic. Most of the cases a pool is needed for different inside local addresses. On the other hand, PAT can work only with one inside global address, but it changes the ports that address is using, and that's because we can that's because in every other that's because we have different private or inside local addresses that are using different ports, and in case one port is being used from a different private address, PAT can change the port address in the translation. Here are some advantages and disadvantages of NAT. In the side of the advantages, we can find that NAT conserves the legally registered addressing scheme. It increases the flexibility of connections to a public network, provides consistency for internal network addressing schemes, and provides network security. On the other hand, the disadvantages of NAT is that performance is degraded, the end-to-end functionality is degraded, the end-to-end IP traceability is lost, tunneling becomes more complicated, and initiating TCP connections can be disrupted. Well, how do we configure these different NATs? Well, for static NAT we have several steps we have to follow. First of all, we have to establish a static translation between private and public addresses. This is that for every inside local addresses we have to have an inside global address. Then the second step is to specify the inside interface. That means which interface is connected to the inside network. Then we have to mark that interface as connected to the inside. Then we have to do the same with the outside interface, and finally we have to mark that interface as an outside interface. Here is an example of a topology that uses a static NAT configuration and the commands display in order to achieve this. And this is like a summary of how NAT process works. Here the client with a public address sends a packet to the web server using a public address. That address reaches R2 R2 router checks its NAT table and decides that the public address is binded to that inside local address, which is the one for the web server, translates it. So in step 3 we can see now that the packet has a private address instead of a public one. It reaches the web server. The web server forwards or sends another packet with its own with its own private address. It reaches the router again, and what the router does is exactly the same. It checks which outside local address it needs, and it changes between a private address to a public address, which now it's going to be directly sent to the client. To configure dynamic NAT, well, we have several steps. The step 1 is to define a global pool, a pool of global addresses, all the public addresses we can gather. The step 2 is to configure a standard access list, so we can allow the private addresses to be translated. Then we have to bind that access list to the pool, so each private addresses know from which public addresses can be assigned. And then we have to identify the interfaces and mark them. In the case of the example, we have that R2 has its own interface. Serial 000 is the inside network interface, and serial 010 is the outside network interface. We can see some of the commands used in order to enable this configuration. First we have to define the public pool, then we have to make the access list, then we have to bind the NAT pool with the access list, and finally, as I've been saying before, identify the interfaces and mark them. Here is like the process of dynamic NAT. We're going to focus only in the orange one. The purple one is the same. Here we have that PC1 sends a packet with a private address. R2 translates it using the first available inside global address. The packet now is sent to the web server with the public address. The server answers with a public address, which comes through R2, which translates it to a private one, so PC1 can receive the packet with its own private network address. Finally, how to configure path. This path configuration is in case we have a NAT pool of addresses or several public addresses from which we can choose. The step 1 is to define the pool of global addresses, so it's the same as dynamic NAT. Then we have to create an access list with all the private addresses that can be translated or that should be translated. Then we have to establish an overload translation. This is the one different step we have to make. Overload is when we changes port numbers. We have to do it by binding the access list with the pool, and by allowing that pool and that access list to work with overload with command IPNAT inside source list, the access list number, the pool name, and activating overload. And finally, we have to do the same we've been doing before with the interfaces, defining which interfaces is the inside network and which one is the outside network. Here is an example of how configuring path is made with a certain topology. But that was for multiple addresses. For a single address, the steps are a few. We have to, of course, define a standard access list. Then we have to establish the dynamic source translation by specifying which access list we're going to use, which is the exit interface, and the overload options. Finally, we have to do the same for the interfaces, which one is the inside interface and which one is the outside interface. As we can see, once we have configured the path with single address configuration, and now only one inside global address is going to act as our public address, but port numbers are going to change thanks to the overload command. How to verify NAT and PAT? Well, actually it's only how to verify NAT. NAT can be static NAT and dynamic NAT can be determined, or we can verify them with the show IP NAT translations, and that command allows us to see like the NAT table that it's enabled at that time. In that table we can see the inside global addresses, the inside local addresses, and in case it is in use or during an active session, we can also see the outside local address and the outside global address. For dynamic NAT we have another command, which is show IP NAT translation verbose. That gives us like a resume or a summary of the activity of that public address or global inside address. There we can see which inside local address has been or is being using that inside global address, the time, the timeout in which that connection is going to expire, and the use count, the entry ID, and the LC entries. It gives us like an extended version of the NAT translations command. Finally, we have important topic which is discussed at the end of the chapter. We have the port forwarding. It's useful for specific services, and it must be done locally at border router. TCP and UDP ports are used. This means that if we have specific services described in our network, we can forward those packets by the port. If we see the example TCP and UDP destination ports, we can see that all addresses using port 23 are going to be forwarded to the telnet server. Meanwhile, all packets all packets using ports 20 and 21 are going to be forwarded to the FTP server, and finally all packets with port 80 are going to be forwarded to the web server. These configurations can be achieved in the router. First, we have to establish an application name. In this case, the example is using a web server. Then we have to know the external port and the internal port. In this case, because it's a web server, we're using the external port 80 and the internal port 80. The protocol being used is TCP. It can be UDP also, and the device IP. This IP address is the one which all packets are being forwarded to. In this case, it's the 192.168.1.254. And this means that all packets with the external port 80 are going to be forwarded to the web server address with internal port 80 using TCP protocol. Well, that's the end of the chapter. I hope you enjoyed it. Thanks for watching.